There's a one thing that we can all agree on. Cheaters are annoying. That dude in Counter-Strike being like, what? Question mark? Hacks? I don't know. And just straight up following. Or a cheated speedrun. It's always frustrating to see that a crazy world record is actually just a fake. Or in relationships. Why did the hacker get banned from the server? Because he couldn't aim for fair play. Got him! Well, all the hate and jokes aside, how does it feel to be in the hacker's shoe? Ha, did you notice I said hackers and not cheaters? Hackers basically the one who hacks the mainframe, does all the research and coding and so on, that basically has the talent to do things, and the cheater is just, yeah. Let's define the idea of hacking. How does it even work? As an example, let's again take Counter-Strike. Have you seen the enemy or not? But internally, the game has to keep track of all enemies, all the stats, their locations, money, and the most importantly, the skins. This means the game stores all of this somewhere inside of your Dell Latitude laptop, and this somewhere is called the memory. The goal of the hacker is to read all of the data from the memory and do something good with it, or bad I guess, I don't know. Sounds pretty simple, right? But there are some caveats. Firstly, the memory looks something like this, and bro, just try to find something here, like for example your health. Oh, well, here it is. The way I knew it is because of this text below, but let's talk about it a little bit later. Sadly for us, the hackers, Papyrus memory is not the same all the time. Your operating system, so Windows for example, will carefully allocate different pieces of the memory to different applications, maybe some modules inside of the applications and so on. This is why we cannot read the same address, the same space in memory all the time and expect to see our health there. A block of memory that Counter-Strike used a second ago could be taken by something else, like a web browser with this video that you're watching right now that you haven't liked yet. And this is why we need the text that I showed before. These are something called offsets. Offsets just represent how far we need to go from the starting point of a game in memory. So let's say the operating system somewhere in the memory allocated a block to it to geometry dash. So that the beginning of this block is our starting point. And exactly this number of steps away, so memory addresses away, I guess, there's a piece of code that makes you die. That sounds wrong. That makes the player die. And we're not only limited to reading the memory, bro, that's boring. We can also write there. So what if we're gonna rewrite the memory at this offset I shown before with something else? Currently the memory around this location looks something like this. And at the first glance it looks like it's gibberish, but there are actually machine instructions with some parameters in there. Each machine instruction has its own individual opcode, and in this case 6A is a push opcode, 8B is a move opcode, and the most important thing for us is the FF opcode, which is a call opcode. As the name suggests, it calls some kind of a reusable piece of code, or simply a function, at the location that is written next to the call opcode. In this case, this is some kind of a geometry dash game engine function called stop action by tag, which in simple words commits the crime of killing you when you absolutely didn't touch the spike. Yeah, continue blaming the game. Anyways, let's replace this sequence with something different. For example, with this. The opcode E9 is a jump opcode, and it's pretty similar to the call, but compared to it, jump doesn't get back to the place where it was called from. So basically, it just changes the flow of the code. And 79060000 is just the address or the location of the end of the game function. So we basically skip the dev. Wow, that was too much nerdness at once. No, my views. And let's finally see what we achieved. And now we're gaming, my guys. We have a no-clip hack. Ho ho ho. Okay, let's proceed with another example. With the soon release of Counter-Strike 2, it only makes sense for me to make something for Minesweeper. Yeah, that makes sense for me. So, we can read memory? We can write memory? Wait, hold on. That gives me an idea. Oh my god, if not this funny 5-second clip or something, I would have been done with that video so fast. Well, actually, this is good content. Let me explain you how this abomination works. How did I even find the offsets in the first place? And oh boy, here it comes. Cheat engine. I feel like everyone at some point of their life played with cheat engine by changing some stats in the game or multiplying your items or so on. But besides just searching the numbers and changing them, you could go a bit more, or actually a huge more. In my case, finding the offsets was extremely trivial. Minesweeper doesn't use something called dynamic memory allocation, which sounds fancy, but this is basically the process of asking your operating system for some money. Wait, Did I just write money in my script? This is the process of asking your operating system for some memory. I almost said money again. And most of the time, operating system will give an app memory quite far away from the starting point of the app itself. This is because some other stuff could have taken the spot next to the app's memory. So operating system will give just a random free chunk of memory to the app. This makes finding offsets a little bit more difficult, but I'm not gonna go too deep into that because, well, we don't need it for this example. I started looking for some obvious and simple places at first, specifically the mines count. I found the location of the mine counter by just changing the amount of them by putting flags, and it allowed me to filter all the garbage out, and I was left with only one location. And as you can see, it actually shows the offset right here, because again, the game doesn't use dynamic allocation, and this address will never change, so no matter how many times I close the game, I open the game, this offset will remain the same. And using the memory view utility, I noticed that there is something interesting just a few addresses away. This is actually the games field, and you can actually see all the mines written as 8F and all the flags I put down as 0Es. So I took the offset of first number 10 here, and my bad apple cheat just writes stuff into this place in memory. Makes sense, right? But we can change the values here all day, but as you can see, nothing will happen. This is because the game draws things only on some events, like clicking, like timer counting up, and us changing bytes in memory won't do anything, of course. And now let me show you the big boy tool. This is a super cool program called Ghidorah, and it is used for the process of decompilation. Whenever programmers build an application, they compile it. Sadly, computers are pretty stupid and they cannot read the human-readable code. Oh, human-readable code! There's something called a compiler, which converts humans-made code into machine code. So the one I showed before was the opcodes and so on. And well, try to guess what decompilation means. Exactly. Sadly, after decompilation, all the human-readable namings for internal properties and function names and so on are lost, because computers don't need this, so why bother? This is why we get quite unreadable code here, but it will do. So I know that there is a function in the game that shows all the mines. I know this because, well, whenever you lose the game, it gets code. You can see all the mines, right? Huh? Wait, what is this? GDI? Oh, that makes things easier for us. GDI is basically a Microsoft thing that is used to draw things on screen pretty easily. Or in the printer. The game obviously has to draw all the mines after you lose. So let's see, where did the function from GDI get called from? There are two places that use one of the GDI functions. First one looks to me like drawing a singular block at specific coordinates. I will rename it to draw block, for example, so I can easily identify it later in other places in code. The second code with the GDI function looks pretty promising. So the game's field is just basically a 2D array with rows and columns. To go through each block, we can iterate through each row, and inside of this iteration loop, we can iterate through each column. So basically, we just have like an X and Y intersection. And this is exactly what's happening in this function here. So let's rename it as a function that does something with the field and see what else it is referenced. Okay, there's one function that references it, so I would assume this is the function that is getting called from the game logic. And yeah, I was right. This function is getting called from another function in game. So as you can see, this function takes some kind of a byte as a parameter, does some logic operations with it later. And previously I showed you how the game's field looks in memory. We saw that the flag ends with 0E or 8E depending on if there's a mine or not. And I see quite a few checks here that mention the E. Okay, so let's take this function and here's the offset of it. Another thing that we as hackers can do is actually call these in-game functions from outside, so from our hack. This is how my bad apple thing works. And I also added a working mine counter and customizable frame width and height as well. And if you're a nerd, the code is in description. And that's it. This is the bad apple hack. And I guess that's it for the video.